Richard James will continue these tutorials on indices with Indices Tutorial Part 2. Here we are manipulating terms that have the same base. Notice that in the case that we have indices represented, we also have the bases that all turn out to be the same. In the numerator, we first multiply the coefficients. In solving this problem, we will first multiply those coefficients, and the coefficients in the numerator are multiplied because we have a multiplication sign right here separating the terms, meaning that we are multiplying these terms. The first step will be to multiply the coefficients, and we have there that 4 times 3 is equal to 12. Now what do we do when we multiply those terms that have the same base? Multiply numbers with the same base by adding the indices. The indices are 2 and 4. 2 plus 4 is equal to 6. So we have c to the power of 6. Notice that we are saying multiply numbers with the same base, but we may have candidates, mathematics campers, or students who will probably argue that these are not numbers. But for the purpose of algebra, they are in the place of numbers, replacing numbers, maybe representing numbers, or we may use them with numbers interchangeably. We just have this single term in the denominator, and that single term returns as it is. We will continue, and this time we will, since we have made or converted or simplified the numerator to one single term, we may proceed to solve the problem by dividing. So we have this single term in the numerator and we have this single term in the denominator. We will therefore divide. Remember that an algebraic term that is not accompanied by any coefficient has a coefficient of 1. The coefficient of the denominator is therefore 1 because initially we have that term in the denominator not accompanied by any coefficient. The default coefficient or the coefficient that we assume is 1. Remember that an algebraic term that is not accompanied by any coefficient has a coefficient of 1. The coefficient of the denominator is therefore 1 because initially the term that we had there was not accompanied by any coefficient. And we have there, well, 12 divided by 1 is equal to 12. That's what we have right there. And the division process will no doubt continue. So there we have the indices highlighted because we need to make use of them when we are dividing. When we divide numbers that have the same base, we subtract the index of the divisor from the index of the dividend. 6 minus 3 is equal to 3. We have it right there, 6 minus 3 is equal to 3, because the index of the divisor is 3 and the index of the dividend is 6. We intend to subtract the index of the divisor from the index of the dividend. 6 minus 3 is equal to 3, and the base will return as it is. It is also important to take note that when we are dividing, we just do not say we subtract the indices. We just do not say that, because subtraction is not commutative. Therefore, we have to be conclusive and we have to be specific to say which one we need to subtract from which. And we are saying it is the index of the divisor that we subtract from the index of the dividend. Here we have another problem involving numbers that have different bases, but they are not easily brought to the same base. We may therefore use another bit of information that we have, such as 9 is equal to 3 to the power of 2, which is this 9 that we have here, are also making use of the fact that 8 is equal to 2 to the power of 3. There is definitely a rule or a principle that we follow that says whenever we are solving a problem that has numbers with different bases, we should actually bring them to the same base before attempting to solve the problem. However, in this particular case, it is not easy for us to bring these numbers to the same base, and it is especially not sensible to attempt that when we have other simpler approaches that we can take. And we will take the approach in which we make use of the fact that 9 is equal to 3 squared and 8 is equal to 2 to the power of 3, or 2 cubed. So we replace 9 with 3 squared and we replace 8 with 2 cubed. Now, what do we have right there? A number with a power raised to another power, or we normally say a number with an index raised to another power. Whenever we have a number with an index that is raised to another power, we multiply the indices. We intend to multiply 2 by a half, but 2 is also a fraction. Any whole number may be written as a fraction with the denominator being 1. And that is what we have done here and will continue to do. So there we are, reducing by a common factor of 2. In the end, we will have 1 divided by 1, which is equal to 1. So this will reduce to 3 to the power of 1. And before we place this one under the microscope, it is possible for us to see that the 3's will cancel and we will have 2 to the power of 2. So multiply those powers and what do we get? No doubt, writing that whole number 3 as 3 over 1. And we will continue to reduce by a common factor of 3. And what do we have left? 2 times 1 is 2. 1 multiplied by 1 here is 1. 2 divided by 1 is 2. So we will have, no doubt, 2 to the power of 2. And make use of another principle that we know when manipulating indices, that any number raised to the power of 0 is equal to 1. There we have it. Finishing up, we say 3 to the power of 1, or any number raised to the power of 1, is equal to that same number. Any number raised to the power of 1 is equal to that same number. No doubt, 2 to the power of 2 is 2 times 2. The power will tell us the number of occurrences of the base that we multiply together. And we have a power of 2. We multiply 2 occurrences of the base together, and the result is 2 times 2, which is equal to 4. Goes right there. And what do we know? Let us, for now, maintain that multiplication by 1 and finish up when we make use of it by saying 3 times 4 is equal to 12, and any number multiplied by 1 is equal to that same number. So we are saying 3 fours, 12. Also, 12 multiplied by 1 is equal to 12. As a matter of fact, any number multiplied by 1 is equal to that same number. There. Here we are manipulating terms that have the same base. Well, we like to have terms that have the same base. We go straight ahead and make use of the principles that are very simple, manipulating terms that have the same base. We can see quite clearly that the numbers in the problem have the same base. We may solve our division problem that involves numbers that have the same base by subtracting the index of the divisor from the index of the dividend. We are making ourselves clear which we subtract from which, and we always subtract in a division problem the index of the divisor from the index of the dividend. We have 18 to the power of 3 minus 2, and 3 minus 2 is equal to 1. Further, any number raised to the power of 1 is equal to itself. 18 to the power of 1 is equal to 18. The index in this problem is 0, and contrary to what is sometimes written, the answer is not 0. Contrary to what is sometimes written, the answer is not 0. Any number raised to the power of 0 is equal to 1. We would definitely like to say irrespective of what the base is. Well, it is true for all numbers with the exception of 0. On a subsequent slide, we will take a look at what we may expect on our calculator if we raise 0 to the power of 0. So we will not take a look at it immediately, but we are saying when we raise a number to the power of 0, the result should be 1 all the time. However, we are also saying that it is not quite right when we are raising 0 to the power of 0, and that we'll take a look at on a subsequent slide. Well, do not imagine that we will do that immediately, but by the time this tutorial is complete, we are sure to take a look at it. In evaluating a number raised to a fractional index, as we have right there, one may jump to use the calculator. However, we may make use of a bit of information that is surely not beyond us. And what is that bit of information? That 25 is equal to 5 to the power of 2. So when we see that fractional index, we are amazed and we are saying, how do these examiners expect us to be able to raise a number to a fractional power? Well, it is not unfair of the examiners, because we should have some bits and pieces of information that can make such a calculation very simple without the use of a calculator. And it is as easy as 25 is equal to 5 raised to the power of 2. So what do? Replace 25 with 5 to the power of 2. Multiply those indices as usual. Whenever we have a number with an index that is raised to another power, we multiply the indices. What will happen? Reduce by a common factor of 2. 3 remains, and we have 5 to the power of 3. And just practicing or reading through instructional materials on indices, we should not find 5 to the power of 3 by any means difficult. And we should be willing and ready to write the answer down as not 75. 75 was crossed out as an incorrect answer. The answer is 125. But let us see what we make of it. The power tells us the number of occurrences of the base that are multiplied together. The power is 3. This tells us that we will multiply together 3 occurrences of 5. So that is what 5 to the power of 3 means. It means that we take 3 occurrences of 5. 5, 5, 5. We multiply those together and we end up with 125. 5 times 5, 25. 5 times 25, 125. And that is our answer. We may also make use of the fact that for a fractional index, the denominator is the root and the numerator is the index. There is no doubt that we have a fractional index right here. For sure, the index is a fraction. The denominator is 2, and that will be the root, and the numerator is 3, and 3 is no doubt retained as the index or power. So we have fractional index, denominator is the root, and the numerator is retained as the power. 2 is the default root. The expression may therefore be written without the 2 in the root position. with or without the 2, we know that the square root is intended. Therefore, this sign that we have right here, if no number is here, then the square root is intended. And that is so with or without the presence of this 2. So we may eliminate it altogether. Now we need to find the square root, and we also need to cube. So we have the square root of 25 to the power of 3, or 25 cubed. We need to find the square root, and we need to cube. We may do any one we choose first. It is sensible to go simple before difficult. So do the one that will result in a simpler number first, and then we may do the other one. Now if we cube 25, that will be 25 multiplied by 25 multiplied by 25, which is a considerably large number. But if we take the square root of 25 first, we will get 5, and we may cube 5 after, because we know the cube of 5 is 5 times 5 times 5, and that will give us 125. So we have chosen to apply the square root first, which is going smaller. So the square root of 25 is 5, and we have 5 cubed right there, which is same as we had on the previous slide, which is the cube of 5 is equal to 125. It would have been a little awkward attempting to cube first, as we have right there 25 cubed is equal to 25 times 25 times 25, which gives 15,625. So that would be going very hard if we intend to do it mentally. To cube 25 to give us 15,625, then attempt to find the square root of that very large number. It would have been a little bit awkward to do that mentally if we are attempting to do the problem mentally, to cube 25 and then find the square root of 15,625. As a matter of fact, arriving at 15,625 mentally, I am sure for most candidates would require that we write some number down. However, if we decided to take the square root first, arriving at 5, and then we cube 5, I am sure that that may be done without a stroke of the pen. So adhere to the old principle that we established in earlier tutorials that suggested to us that we go simple before we go difficult, and that is one that we should take advantage of. There is a striking resemblance with this problem and the one before it. As a matter of fact, only the bases are different. This, however, does not affect the analogy in any way, as it is only that 25 is equal to 5 squared, and that is replaced with 4 is equal to 2 squared. So the analogy is very, very close. So replace 4 with 2 squared. Then do the exact same thing. Multiply the indices. the indices are the same, again reduced by a common factor of 2, then we will result in 2 to the power of 3. What do we do after that? The power tells us the number of occurrences of the base that are multiplied together. The power is 3. This tells us that we will multiply together 3 occurrences of 2. So 2 to the power of 3 is equal to 2 times 2 times 2, which is actually equal to 8. 2 times 2, 4. 4 times 2, 8. And that is all there is to it. We may also make use of the fact that for a fractional index, we are taking the analogy also to the second attempt in solving the problem. So we are also making use of the fact that for a fractional index, the denominator is the root and the numerator is the index. Same way we are approaching this problem, no different. And if we can remember, because in mathematics we do not have to invent the wheel. If it is exactly the same thing, then we do exactly the same thing. We only make note of the differences and adjust our solution accordingly. So with or without the 2, we are sure that the square root is intended. As a matter of fact, retaining it is a case of redundancy. So you write, so that is a case of redundancy, retaining that 2, so we eliminate that all together. There is a principle that we apply in previous tutorials. Go easy before going hard. It is better to find the square root before cubing. So we will find the square root of 4, which is 2. Then we cube 2. 2 to the power of 3 is equal to 8. And that is all there is to it. The cube of 4 is not so horrible. 4 cubed is equal to 4 times 4 times 4, which is equal to 64. So in this particular case, it might not have mattered seriously the one that we do first, because if we cube 4, we just get only 64, and the square root of 64 is 8. So the small numbers should not affect the process much, irrespective of the one that we do first. So in this particular case, whether we cube or we find the square root, that should not be too much of a concern, because the numbers are not very large, and as a matter of fact they are not unfamiliar. Let us make use of the fact that a number with a negative index may be reciprocated and the sign of the index changed to positive. So we may do that when we have a negative index. We may do the reciprocal and change the sign of the index to positive. And everything inside of that bracket is being multiplied by 2. Everything inside of the brackets is raised to the power of 2. We will raise each one to the power of 2. So we will, because this entire thing is enclosed in brackets, the entire fraction is raised to the power of 2. We may raise a fraction to the power of 2 or any other power for that matter by raising the numerator to the power of 2 and also raising the denominator to the power of 2. 3 to the power of 2, 5 to the power of 2, and we may finish up by squaring both numerator and denominator. 3 squared is equal to 9 and 5 squared is equal to 25. We will take 2 shots at this problem. In our first attempt, we will make use of the fact that when multiplying numbers that have the same base, we add the indices. When multiplying numbers that have the same base, we add the indices. There we go. What do we notice? 2 is not raised to any power. The power that we assume is 1, and we do not only assume it, we also place it there temporarily. If a number is not accompanied by an index, then the index that we assume is 1. Also, 0 plus 1 is equal to 1. So we are adding those indices. 0 plus 1 is equal to 1. Adding the indices is what we do when we multiply numbers that have the same base. So the result is 2 to the power of 1, and any number raised to the power of 1 is equal to itself. And that is all there is to it. Or we may say 2 to the power of 0 is equal to 1. So we may now make use of the fact that any number raised to the power of 0 is equal to 1. Therefore, in the place of 2 to the power of 0, we write 1. And also, any number multiplied by 1 is equal to that same number. So 2 times 1 is equal to 2. That's all there is to it. Again, a number with a negative index may be reciprocated and the sign of the index changed to positive. But first of all, let us be reminded that a whole number may be written as a fraction with a denominator of 1. So let us write 5 as a fraction with a denominator of 1. Then we reciprocate that fraction and change the sign of the index. And we have 1/5 to the power of 2. Again, everything inside of the brackets is raised to the power of 2. We will raise each one to the power of 2. 1 squared, or 1 to any power, is always equal to 1. So we may finish up by squaring both numerator and denominator. 1 squared is equal to 1, and 5 squared is equal to 25. 1 over 25. By now, we should be solving these kinds of problems spontaneously. We will first make an attempt in which we solve it like the way that we solved the others. So we have 49 to the power of a half. How did we solve the others? We solved the others that are accompanied by a fractional index by making use, when we can, of another bit of information. For example, 49 is 7 raised to the power of 2. So replace 49 with 7 raised to the power of 2. And that whole number 2 is a fraction whose denominator is 1. And that is what we will write when we are multiplying those numbers, because whenever we have a number with an index that is raised to another power, we multiply the indices. So we have those 2's are gone, reducing by a common factor of 2, and we have 7 to the power of 1, and any number raised to the power of 1 is equal to that same number. That's all there is to it. 49 to the power of a half. What do we do next? We may also make use of the fact that the square root and the power of a half are interchangeable. So we may replace the power of a half with the square root. And what do we mean by the square root of 49? The square root of 49 is that number that you multiply by itself, and the result is 49. What number do we multiply by itself and the result is 49? Maybe a better question to ask, is for square root. Square root is related to 2, and the square is related to 2. So in inquiring about the square root of 49, we may say, what number do we multiply 2 occurrences of? And the result is 49. And we multiply 2 occurrences of 7, and the result is 49. Therefore, the square root of 49 is equal to 7. There is nothing to it. This problem may be shown to be quite similar to many others that we have solved before, both in this tutorial and the other. So this one may be shown to be quite similar to many others that we have solved before, after we make use of the fact that we have 3 occurrences of the same thing being multiplied together, which will mean that it is raised to the power of 3. So we have 6 to the power of 2/3, and the same thing occurring here and here also. Therefore, if we are multiplying 3 occurrences of the same thing, then we know that we are cubing that same thing that we have right there. 1, 2, 3. So 1, 2, 3. So we have actually 3 occurrences. Therefore, what we have right there is 6 to the power of 2/3 raised to the power of 3. And remember that when we have a power raised to another power, we multiply the indices and reduce by a common factor of 3. All that is left is 2. Come on, 6 to the power of 2. 2 occurrences of 6 multiplying together. The value of 6 raised to the power of 2, or 6 squared, may be found by multiplying 2 occurrences of 6 together. 6 multiplied by 6 is equal to 36. No one is amazed. I attempted to find another sensible way to solve the problem, but no other way was very plausible. I am sure that we could have found other means of solving the problem, but the other means, those would not have made as much sense, or would have been more logical than the ones that we have right here. So we may make use of the information that we have right here. As a matter of fact, the power of 2/3 makes this problem somewhat difficult, because it is not possible to find the cube root of 6 quite easily without the use of a calculator. But although 6 to the power of 2/3 in itself or of itself is difficult, the context or the situation that it is used in makes it very simple, because we have 3 occurrences. Therefore, we raise to the power of 3, multiply the indices, and the 3's will be eliminated by reducing by a common factor of 3. Therefore, in the end, the problem turned out to be not so difficult. This is a direct analogy to a previous problem. This is a direct analogy to a previous problem. And what do we know? We can see quite clearly that the numbers in the problem have the same base. We may solve our division problem that involves numbers that have the same base by subtracting the index of the divisor from the index of the dividend. And I am highlighting that we need to say which one we subtract from which. We just do not go ahead and say subtract the indices, because what will happen most times is that if the index of the divisor is greater than the index of the dividend, candidate usually subtract the smaller one from the larger one, thereby making a mistake. So we need to always be mindful of the fact that we need to subtract the index of the divisor from the index of the dividend. So we have 4 minus 3 is equal to 1, and what? Any number raised to the power of 1 is equal to itself. The index in this problem is 0, and contrary to what is sometimes written, the answer is not 0. Any number raised to the power of 0 is equal to 1. So 6 raised to the power of 0 is equal to 1. And I think that some way along the way we had 8 raised to the power of 0, or was it 18? But any number raised to the power of 0 is equal to 1. And we are making that statement not ignorant of the fact that when we raise 0 to the power of 0, we may have some difficulty. So as long as it is not 0, then the result is 1. 0, because of its peculiar qualities, is responsible for a lot of exceptions in mathematics. At this level, we are only beginning to see some of them. For example, any number divided by itself is equal to 1. 4 divided by 4 is equal to 1. -7 divided by -7 is equal to 1. Even in algebra, n divided by n is equal to 1. For 0, this is not true. The power of 0 is another example. 0 raised to the power of 0 poses some problem. So we are saying that at this level we are only beginning to see some of the exceptions in mathematics that are caused by the presence of 0. And we are saying that we divide anything by itself and the result is 1. But when we divide 0 by 0, that poses a problem, and we will take a look at that on a subsequent slide. In solving this problem, we may take quite a few steps. In some cases, the steps may be reversed. Again, we have a negative index, and we have that whole number that may be given a denominator of 1. So we have a negative index, and we intend to write it as its reciprocal and change the sign to positive, like so. Everything inside of the brackets is raised to the power of a half. We will raise each one to the power of a half. 1 to the power of a half, 1 raised to any power is 1, and 16 to the power of a half is the same as the square root of 16, which is equal to 4. The square root and the power of a half may be used interchangeably. 1 to the power of a half is the same thing as the square root of 1, which is equal to 1. And 16 to the power of a half is equal to the square root of 16, and that is equal to 4. We may also take the same approach as we have on the script, which is the one that we have right here, because the one that we took just now actually is not this one. So we may now take the same approach as we have on the script, in which we make use of the fact that 16 is equal to 2 to the power of 4. So replace 16 with 2 to the power of 4, and what do? Multiply the indices. Whenever we have a number with an index that is raised to another power, we multiply the indices and we reduce by a common factor of 2. 2 into 2 is 1, and 2 into 4 is 2. And do not forget this negative sign right here. So we have 2 to the power of negative 2. And what do we do with that 2 to the power of negative 2? A number with a negative index may be reciprocated. The sign of the index changed. And we are making, before we do the reciprocal, that we are making use of the fact that 2, a whole number, is 2 over 1, and then we go straight ahead. And what do we do after that? Each one is to be raised to the power of 2, because we intend to raise this entire fraction to the second power. And how do we do that? By raising the numerator to the second power and raising the denominator to the second power. Square both the numerator and the denominator. 1 squared is not 2. 1 squared is 1. 1 squared is actually 1 multiplied by 1, and that gives 1. And 2 squared is actually 2 times 2, which is equal to 4. So we will take a look at some of the statements that we made earlier on that we will take a look at on a subsequent slide. We are investigating the reason for 0 raised to the power of 0 being undefined. That is what we are doing. We are investigating the reason for 0 raised to the power of 0 being undefined. As a matter of fact, if you input the expression 0 to the power of 0 into your calculator, then you will get an error message. Before we do that, let us demonstrate why we will get the same result when we input the result 0 divided by 0 into the calculator. So we intend to investigate the reason for 0 raised to the power of 0 being undefined. That is what we are about to do. But before we do that, let us demonstrate why we will get the same result when we input the result 0 divided by 0 into the calculator. What we have there is 15 divided by 15 is equal to 1, and we imagine the same thing for any number. 4 divided by 4 is equal to 1. So let us say that it is true. 0 divided by 0 is equal to 1. Because if we divide a number by itself, the result is 1. So first of all, any number divided by itself is equal to 1. Let us assume that it is possibly true for 0. 0 divided by 0 is equal to 1. Because any number divided by itself is equal to 1. What do we have there? 7 divided by 0 is equal to infinity. A number that is so large, it is infinitely large and undefined. What do we imagine? Any number divided by 0 results in a number that is infinitely large. So what do we say then? It should also be true that any number divided by 0 results in an answer that is infinitely large. Such a number does not exist. But let us assume that the same is true for 0 divided by 0. So 0 divided by 0 is equal to infinity also, because any number divided by 0 results in a number that is infinitely large or indefinitely large. The argument is that, and we are talking about why do we say that when we divide a number by 0, we end up with a number that is indefinitely large. Why is that so? And the argument is that if we continue to divide by a smaller number, then the quotient will continue to increase. So if we continue to divide by a smaller number, then the quotient will continue to increase. So if we divide 12 by 12, the result is 1. So divide by 6, which is a smaller number, 2. So we are increasing. Smaller yet is 4. If we divide 12 by 4, we get a larger number. Even smaller than 4 is 3. When we divide by 3, we get a larger number still. Notice that the answer is increasing when we decrease the number that we are dividing by. Smaller still if we divide by 2. 12 divided by 2 is equal to 6. And 12 divided by 1 is equal to 12. Therefore, if we divide by a number that is indefinitely small, then the result will be indefinitely large. Infinity is the name given to the number that is indefinitely large, which is the number that we get when we divide by 0, because 0 is indefinitely small. So the number that we get when we divide by 0 is indefinitely large, and we represent that by infinity. What about this one? Another one, 0 divided by 20 is equal to 0. Finally, if we divide 0 by any number, the result is 0. So let us say that the result is also true when we divide 0 by 0. 0 divided by 0 is equal to 0. So if we follow all of those three definitions, then we will get those three results. Any number divided by itself is 1. So 0 divided by 0 is 1. Any number divided by 0 results in an answer that is indefinitely large. Dividing by 0 here again, but we are dividing 0 by 0. Indefinitely large. No problem. Here we go again. If we divide 0 by any other number, the result is 0. So here is 0, and we are dividing by some number. We expect that the result is 0 also. What do we know? Take a look at those. Apart from the fact that infinity is already an indefinite answer, the ambiguity is compounded by the fact that we have three possible answers according to the definitions in mathematics. Therefore, the only surety is that 0 divided by 0 is undefined. This answer is already of itself a problem, a number that does not exist, one that is indefinitely large. This answer of itself is a problem, but compounding the problem, we have two other answers that are different. They are different from infinity, and they are different from each other. Therefore, the only surety is that when we divide 0 by 0, we get an answer, or we do not get an answer. The result is undefined. We may find the result that 0 divided by 0 is undefined to be quite useful in showing why 0 raised to the power of 0 is also undefined. So, the fact that 0 divided by 0 is undefined, that fact may be used in showing why 0 raised to the power of 0 is undefined. So consider the problem that we have right there, which is 15 to the power of 1 divided by 15 to the power of 1. We are dividing. So when we divide, we subtract the index of the divisor from the index of the dividend. 1 minus 1 is equal to 0. Any number raised to the power of 0 is equal to 1. What do we do next? Let us do the same for 0. 0 raised to the power of 1 divided by 0 to the power of 1. So we have 15 raised to the power of 1 divided by 15 to the power of 1. Subtract the indices. 15 raised to the power of 0. Any number raised to the power of 0 is equal to 1. So subtract the index of the divisor from the index of the dividend, and we get that is equal to 0 to the power of 1 minus 1. So we have right there 0 raised to the power of 1 minus 1, which is equal to 0 to the power of 0, which we imagine to follow suit from right here to give any number raised to the power of 0 is equal to 1. If we follow this exactly. So if we follow the logic from the previous example, then the result should follow suit. Same way that we have right here 0 to the power of 1 divided by 0 to the power of 1 is also following from 15 to the power of 1 divided by 15 to the power of 1. However, we know that any number raised to the power of 1 is equal to itself. So 0 raised to the power of 1 is equal to 0. Therefore, so what we are saying is that any number raised to the power of 1 is equal to itself. So what we have here is 0 to the power of 1 and 0 raised to the power of 1. So 0 raised to the power of 1 is 0. 0 raised to the power of 1, 0 raised to the power of 1. This is 0, this is 0, because any number raised to the power of 1 is equal to itself. So that turns out to actually be 0 divided by 0. So 0 raised to the power of 1 divided by 0 raised to the power of 1. If we follow the logic from right here, should be equal to 1. However, any number raised to the power of 1 is equal to itself. So 0 to the power of 1 divided by 0 to the power of 1 will be 0 divided by 0. Since 0 to the power of 1, which is the same thing we have here, divided by 0 to the power of 1 is equal to 0 to the power of 0. That is what we have right here. And 0 to the power of 1 divided by 0 to the power of 1, because any number raised to the power of 1 is equal to itself. This 0 to the power of 1 divided by 0 to the power of 1, 0 divided by 0, which is undefined. All three of them are equal and undefined. Therefore, 0 to the power of 0 is also undefined. So let us see why again 0 to the power of 0 is undefined. It is undefined because 0 to the power of 1 divided by 0 to the power of 1, which is what we have here. If we subtract the indices, we get 0 to the power of 0. But if we make use of the fact that any number raised to the power of 1 is equal to itself, we will get 0 divided by 0. Therefore, 0 to the power of 0 is also equal to 0 divided by 0, because these two should be equal. So 0 to the power of 0 is actually equal to 0 divided by 0, and this is undefined. Therefore, 0 raised to the power of 0 is not actually 1, but is actually undefined. A common error that students make is that they multiply the bases as well as add the indices when they are multiplying numbers that have the same base. For example, they multiply the bases and add the indices when multiplying numbers that have the same base. So they go and they say, multiply the bases. They multiply the bases. 3 times 3 is equal to 9. And they go ahead and do what they should. Add the indices. 2 plus 4 is equal to 6. And they are happy. 9 to the power of 6. I cannot get it wrong, but I am sure that it is wrong. The correct thing would have been that the base is unaffected. the base will go back just as it is. Then what do we do? Then the indices are added. So 3 to the power of 6. Let us prove that the second take on the problem is correct, which is 3 to the power of 6. Let us rewrite the multiplicand and the multiplier in their flattened form, and we mean expanded form. The index will tell us the number of occurrences of the base that are multiplied together. So 3 to the power of 2, 2 occurrences of 3, 3 times 3. 3 to the power of 4, 4 occurrences of 3, 3 times 3 times 3 times 3. So we have 1, 2, 3, 4 of them. So there is our problem under the microscope. We will replace 3 to the power of 2 with 2 occurrences of 3. And what will we do next? Replace 3 to the power of 4 with 4 occurrences of 3. And what do we have there altogether? I am sure that what you have right there is 6 occurrences of 3, which turns out to be 3 to the power of 6, and not 6 occurrences of 9 that gave the incorrect answer, which is 9 to the power of 6. So I am sure that when we put everything under the microscope, going to the most basic level and building it from the foundation, we realize that what it actually turns out to be is 3 to the power of 6 and not 9 to the power of 6. You can check your answer in any way you please. Maybe you will want to use the result from your calculator as a confirmation, or you may rely on your memory. In Richard James Mathematics Resources, we have a table of powers of 3 that ended at 3 to the power of 6 is equal to 729. Irrespective of how you will prove the point, do not multiply the bases when attempting to multiply numbers that have the same base. Add the indices only. The base will return as it is, as we have it right here. So we may make use of the fact that 3 to the power of 6 is equal to 729. Maybe you want to say 3 squared is 9, and 3 to the power of 4 is 81. 9 multiplied by 81 is 729, which is 3 to the power of 6. You may dabble a bit in any way you please with these digits in order to satisfy yourself that 3 to the power of 6, which is equal to 729, is the correct answer, because it really is. We will continue to highlight the inaccuracy of multiplying the bases when multiplying numbers that have the same base by assuming that we will do a similar thing when dividing. So we will continue to highlight the inaccuracy of multiplying the bases when multiplying numbers that have the same base by assuming that we will do a similar thing when dividing. So there we are, dividing numbers with the same base. What do? Well, if when we are multiplying, we multiply the bases, which is not correct by any means, then when we are dividing, we should divide the bases also. If when multiplying numbers that have the same base, we multiply the bases, then when divide numbers that have the same base, we will also divide the bases. So 3 divided by 3 is equal to 1. And what do we do with the indices? Also, when dividing numbers that have the same base, we subtract the index of the divisor from the index of the dividend, and we have 4 minus 2, which is equal to 2. 1 to the power of 2. 1 raised to any power is equal to 1. 1 raised to any power is equal to 1. The answer will therefore be 1. That we know to be incorrect. What do we do next? The correct thing would have been that the base is unaffected. There it is, going back as it is. So the correct thing would have been that the base is unaffected, and the index of the divisor is subtracted from the index of the dividend. So we have 4 minus 2 is equal to 2. That would have been the correct answer. Let us prove that the second take on the problem is correct. Let us rewrite the dividend and the divisor in their flattened form or expanded form. The index will tell us the number of occurrences of the base that are multiplied together, and we have that 3 squared, or 3 to the power of 2. We multiply 2 occurrences of 3, 3 times 3. And for 3 to the power of 4, we multiply 4 occurrences of 3. Replace 3 squared with 2 occurrences of 3. Replace 3 to the power of 4 with 4 occurrences of 3. And no doubt we may reduce that fraction, and we may do that by reducing by a common factor of 3. And again reduce by a common factor of 3. What do we have there? Do we have 1 to the power of 2 or 2 occurrences of 1? No. What we have there is 2 occurrences of 3 that turn out to be 3 squared and not 2 occurrences of 1. That gives the erroneous answer 1 squared. So what we have right here is 2 occurrences of 3, which is 3 times 3, 9, or we may say 3 squared, which is equal to 9. And we have that instead of the incorrect answer, 1 squared. Also, if we divide 3 to the power of 4, which is equal to 81, by 3 to the power of 2, which is equal to 9, then we get 81 divided by 9 is equal to 9. Also, 9 is equal to 3 to the power of 2, 3 times 3. As a matter of fact, one could not imagine that the answer that requires us to divide the bases when dividing numbers that have the same base could ever be correct. This is so because in every single case, the answer will turn out to be 1, irrespective of the index of the dividend and the index of the divisor, because we would have been dividing in every single case, because we say we are dividing numbers that have the same base. Therefore, if they are the same, when we divide one by the other, we will get 1. 1 raised to any power is 1, and that we will get irrespective of what the base is, because we will be dividing the bases that are equal. The result is always going to be 1. what I have done is that I have shown that what is good for the goose is also good for the gander. That is what I am making use of. If one imagine that it can be correct to multiply the bases when multiplying numbers that have the same base, then it will also be correct to divide the bases when dividing numbers that have the same base. Both are wrong. The first one may get by a few candidates. The second one is astonishingly wrong. Therefore, making the connection with the first and striking the analogy, we would have to logically come to the conclusion that the first one is also wrong. So, both of them are wrong, and of course one would definitely follow from the other. The first one may give a result that is not so strange, not so alarming, not so glaring, but the second one, the answer is always going to be way off. Therefore, if we take our tip from the second one that is astonishingly wrong, remember that both of them are related, then if one is wrong, so is the other.